our seats, please, so we can start. Here what Greg has to say about black holes.
I know who she is. Can you sign Michelle Phillips?
We can have everyone's attention now. We start our meeting event. Dr. Greg Salvesen. Greg Salvesen is a postdoc at UCSB. The theme of his research is to combine observations and theory to study black hole X-ray binaries, whose anatomy consists of a black hole feeding from a companion star. Greg grew up on the East Coast and made his way to the West Coast, with some stops along the way. First to Ann Arbor, Michigan as an undergraduate, where he became an astronomer, and then to Boulder, Colorado, for graduate school, where he became a long-distance runner. Shamefully, I don't know, this isn't shameful. A lot of people don't own a telescope. Anyway, Greg says, shamefully, Greg has never owned a telescope.
You can join and borrow one.
Yes.
Join the club.
Right.
Join the club.
Hoping to change that, Greg would welcome recommendations in anticipation of his imminent move to the dark skies of northern New Mexico. So let's have a warm welcome to Dr. Greg.
Is the microphone on? It sounds like it's on.
No. Nope.
Yes. Yes.
Better.
Is it good? Can you hear me through the microphone or not so much?
You gonna leave the light partially in?
That's all right. Well, I won't take offense if you fall asleep. I won't even I can't see. Okay, I'll try to talk loud because I'm not sure the mic is working and I have it as close to my mouth as I can possibly make it. So my talk tonight, I'm going to talk about something you might not have heard too much about before is how black holes spin. You might have heard that black holes have mass and there can be big black holes and little black holes. But I want to talk about black hole spin tonight. And what I'm showing you here is actually a picture of a black hole. It was the first ever prediction of what a black hole might look like. So the idea here is if you have a disk of gas around the black hole, we call that a clothed black hole as opposed to a naked black hole. If you have a disk of gas that emits light, that light gets bent in all crazy ways, such that you see a kind of asymmetric, distorted-looking thing like this. And this is a prediction back from 1979. And believe it or not, this black hole is not spinning. So it turns out these kind of images, like we got recently, and I'll talk about a little bit in the talk, it's hard for them to give you much information about the spin of a black hole, but it's still incredible confirmation of a black hole when we're able to see something that remotely resembles this image. So I just wanted to put this up as kind of motivation. And the guy who made this, he, every single one of these dots that you see, he actually drew by hand and then took a photograph of it and sort of took a negative of that photograph. So he had a computer calculate where every single one of those dots should be, and he drew them all by hand.
Oh my God.
Okay. All right. So I thought we could start this talk by taking what I'll call a safari, a black hole safari. And I'll sort of try to convey that black holes are everywhere in the universe. And not too long ago, 40 years ago or so, people were skeptical that black holes even existed. But you'd be a crackpot in the astronomy community today to deny their existence. And really, we think they're everywhere. So much so that the Hubble Space Telescope spent 11 days, not continuously, but over time, a total of 11 11 days staring at a tiny patch of sky, and really a tiny patch of sky. So tiny that if you held a penny out at arm's length and you look through Lincoln's eyeball, that's the size of the patch of sky we're talking about. It's tiny.
Wow.
And it was one of the darkest patches of sky that we knew about. Hubble stared at it for 11 days, and this is what it saw. And every single point of light that you see in this image is a galaxy. And every galaxy contains hundreds of billions of stars, and now we think that every star has about a planet or so. So it's just nuts. So if you extrapolate all 10,000 galaxies, and you take that, Lincoln's eyeball, and you stitch it up across the entire sky, we think there's something like, now I'm forgetting the number. I think it was something like 200 trillion galaxies in the universe. It's a number that doesn't even mean anything. It wouldn't matter what I said, right?
Space
But it's just ridiculous. And we think that every single one of these galaxies, with a few exceptions, at its center hosts a supermassive black hole, ranging in size from about 1 million times the mass of the sun to about 10 billion times the mass of the sun. Also just like huge numbers that kind of don't mean anything to us. So for the first time ever, we got a look at the black hole in a galaxy close to us. That galaxy is called M87. And at the center of that galaxy is a supermassive black hole. That black hole is about 6.5 billion times the mass of the sun, right? That's like, there's something like 6.5 billion people alive, right? It's ridiculous. And the signature, if you remember from the title slide, is this kind of asymmetric emission, right? So there's some gas orbiting around the black hole in some way that we're not totally sure about, but we're able to see this asymmetry, and that's the signature for gas emitting around a black hole. And because we don't see emission in the central region here, that's what we call the event horizon of the black hole, which I'll get to in a minute. But because it's dark here, that's additional evidence for this being truly a black hole. And to give you a size of scale, this is a little cartoon. If we put our sun at the center of the black hole, and this is where Pluto is, and this is where Voyager 1 is, I mean, our entire solar system fits very comfortably within this black hole. This black hole is huge, okay? But it's also cramming an incredible amount of mass into a fairly small space. Depends how you look at it. Okay, 6.5 billion times the mass of the sun. We can also look at the black hole at the center of our own galaxy, the Milky Way. The name of the black hole is Sagittarius A star. And the way we can measure the mass of the black hole at the center of our galaxy is to trace the orbits of individual stars. So we spend like 2 decades or 3 decades or however long we possibly can just looking how stars orbit around the center of the galaxy. And we can use those orbital dynamics to work out that the thing they're orbiting about, which we don't see any light coming from, whatever this thing is, has to be about 4 million times the mass of the sun. So we're able to very precisely measure the mass of our own black hole at the center of our own galaxy, and it's totally wimpy in comparison to most supermassive black holes. It's only 4 million times the mass of the sun. That other black hole is 1,000 times more massive. So our galaxy hosts a pretty wimpy supermassive black hole. And this is all done at a group at UCLA. They're the powerhouse for this project, the California Pride. Okay, so those are the supermassive black holes. But within any given galaxy, there are millions to hundreds of millions of black holes just zipping around through every single galaxy. And these are much smaller. They're maybe between 5 and, well, maybe up to 100, we think now, times the mass of the sun. And what I'm showing you here, it looks like there are about a dozen of these black holes, where we now know, for these black holes, we know A, that they're black holes for sure, because we're able to measure their mass, and their mass is big enough that we can say it has to be a black hole. And we're also able to measure where are in space, and also their velocity in space, their 3D velocity in space. And we've done that for all these guys. And you can see they're kind of whizzing around everywhere. And there are maybe about another dozen or so black holes where we know their position and their masses, but we don't know their velocities. So there are maybe another dozen black holes that we can't put on this plot yet. But so maybe we know of about 2 dozen of these, what are called stellar mass black holes, because they're roughly, 10 times the mass of the sun or so. We know about 2 dozen of them in our own galaxy. And we think every galaxy has loads of these things. Okay. Now, what kind of talk on black holes is complete without an attempt to explain what a black hole is? So that's what I'm going to do now in the next couple of slides before launching into how we measure the spins of the black holes. So the thing I want to emphasize right up front is gravity. A black hole is basically gravity's victory. It's gravity saying I've won. All right? So here, let's talk about the gravitational force briefly. If I've got 2 objects some distance apart, right? This guy, and they're separated apart, the gravitational force that one of those objects exerts on the other object is proportional to 1 divided by the distance between them squared. Okay? So if I bring them closer and closer and closer, they are more strongly and strongly attracted to each other. All right? So the closer they get, the more and more and more they want to be attracted to each other. And if there's nothing to stop them from smashing together, then they will. So when I say that the gravitational force is not self-limiting, what that means is there's nothing to stop it. Like once it gets going, it wants to bring these 2 objects together. Okay? Or suppose you had a star, right? The gravity of that star wants it to collapse to a point, okay? Which is what I'm trying to show here. So this is analogous to this situation. So if I consider just a point on the surface of this sphere, or this star, if I start forcing that sphere to contract, the gravitational force felt by this thing on the surface gets stronger and stronger and stronger, and it's a runaway process. The more I collapse a thing, the stronger and stronger and stronger the gravity is on its surface. And it will just collapse to a point unless there's something there to stop it. And in stars, the thing that's there to stop it is at the center of the star, we have nuclear fusion going on, and that heats up the star, and high temperatures in the core of the star also cause high pressures. So the pressure that's ultimately driven by these nuclear reactions at the center of the star, this pressure is fighting back against gravity. But at some point, we run out of fuel in the star. It's going to take a long, long time, like for the sun, another 5 billion years or something. But at some point, we run out of this pressure support against gravity, and then gravity is just going to want to collapse the thing. In the case of our star, the star is not going to become a black hole. There is some complications, but generally, the message is, if there's nothing to stop gravity, it will just continue to want to attract 2 things together, or continue to want to collapse. Okay. Now, let's take the Earth as an example right now. So this is the Earth, and if I have a ball, okay, and I throw it straight up, if I'm really strong, and I can throw it 11 kilometers per second, which is, like 6 miles a second, or 7 miles a second. If I can throw something, or make something go that fast, then it will escape the Earth forever and never come back. If I can't throw it quite that fast, it'll get really, really, really high, and it'll be slowing down as it's getting higher and higher and higher, and then fall back down. Right? We're familiar with this. You throw a ball up, it gets to some height before it falls down. You throw it harder, it gets a little higher. At some point, if you threw it hard enough, it wouldn't come back down. And the velocity at which you need to throw the thing to have it totally escape is called the escape velocity. That's the velocity where it would never fall back in. And that velocity depends on the compactness of this body, in this case the Earth. So what if we made the Earth 100 times smaller in size? So here, the radius of the Earth is 6,500 kilometers. Let's make it 65 kilometers. All right? So what that does, changing the radius of the Earth by a factor of 100, increases the escape velocity by a factor of the square root of 100, which is 10. So now, if we want something to escape this shrunken, compressed Earth, we need to throw it 10 times faster than before for it to escape. Okay? And we can just keep doing this, keep compressing the Earth further and further and further. What if we compress it to 1/3 of an inch? Really small. If somehow you could compress the Earth to like the size of a marble, then you'd be hard-pressed to have anything, anything you threw up would have to have such a spectacular velocity to escape. You could barely escape the Earth if you sent something going at the speed of light. Okay? And so what a black hole is something that's so compact that if you wanted to have something escape from its surface, it would have to be moving faster than the speed of light. And that's when you get a black hole. Okay?
Great.
All right. Now, black holes can have mass, and the mass of the black hole curves space-time. So maybe you've seen these kind of attempts to explain like what black holes are before with these kind of rubber sheet analogies. So what a black hole does, it curves space-time and distorts it like this, and this kind of this well down here kind of goes on, and the boundary of this well is what we call the event horizon of the black hole. And inside is the singularity. So interior to this event horizon, once you cross through the event horizon, everything just wants to go to the singularity of the black hole, a single point. All right? And black holes obey the Las Vegas rule. Okay? Anything that happens inside of a black hole stays inside of the black hole. There's no way to get it out. Once you cross through the event horizon, you're destined to go to that singularity. But the funny thing about the event horizon is it's not a physical surface. It's just a special location we use to pretty much say, like, interior to the event horizon, you're destined to go to the singularity. Exterior to the event horizon, you can get out and escape the black hole if you can somehow, get your rocket ship to go really, really fast. But in actuality, if you were traveling into a black hole, well, there's a caveat here. If you were traveling into a very, very massive black hole, you wouldn't even notice that you crossed into the event horizon. I think I worked this out once. Like, as long as the black hole is something like 20,000 times the mass of the sun or more, you could survive passing through it. You'd die right after that, but it's sort of counterintuitive. The more massive the black hole is, the less it's going to hurt passing through the event horizon. Okay. And I should say, and again, you wouldn't even notice it. Like, there's nothing special about the event horizon in that way. It's not like a physical surface, like the surface of the Earth. And there's actually observational evidence for this, believe it or not, which I'm happy to discuss later on in questions if you're interested. Okay. There's also no physical limit as to how big or small in mass a black hole can be. So, like I said, if we can somehow crush the Earth to the size of a marble, it'll become a black hole. If you take any object you want, if you can crush it small enough, it will become a black hole. In nature, we observe sort of two types of black holes generally. The ones that I showed you earlier, called supermassive black holes, which have masses anywhere from about 1 million to 10 billion times the mass of the sun, and also these stellar mass black holes, which are the remnants of dying stars, and they have anywhere from like 5 to 100 times the mass of the sun. There was a talk here a couple months ago by Omer Blaze, and I think he talked about these sources called ULXs, which are ultraluminous X-ray sources. And for a long time, astronomers thought they either had to be these stellar, and so what an ultraluminous X-ray source is, it's just something that's so insanely bright. How is it so bright? One way to do it is if it's gas in the vicinity of a stellar mass black hole that somehow gets like channeled into a very collimated beam. That's one way to do it. Another way to do it is if the gas is orbiting around a black hole that has a mass intermediate between these two regimes. And it turned out to be neither of those answers. As far as we can tell, the ULXs that we know about are neutron stars, which was a big surprise. And I think that's what Omer's talk was about. But as of yet, astronomers do not have compelling evidence for the existence of black holes with some kind of intermediate mass between these two, which is really weird because, you know, we think in order to get to 1 million or 10 billion times the mass of the sun, you've somehow got to like go through an intermediate mass phase. But as of yet, we haven't detected any. It's very hard to do. Okay. Black holes can also have spin, and this spin twists the space-time. So before we saw that the black hole mass curves it, but what you can kind of see here is that now this grid is twisted as well. All right? And that's the effect that black hole spin has. And this twisting of space-time, if you're orbiting close to the black hole, if I'm just sticking my arms out and there's a spinning black hole at the center of the stage and I'm orbiting around it, the black hole will force me to start spinning as I'm rotating. If the black hole's spinning, it will force objects orbiting about it to rotate because it's twisting up the space-time. And if I can somehow, I'm not inside the black hole yet, right? I'm out here somewhere. If I can somehow escape from the black hole by going really fast, like almost the speed of light, then I can actually, that rotational energy that the black hole gave me, I carry that along with me, and that actually slows the rotation of the black hole. I've, in a sense, stolen some of its rotational energy. So over time, black holes can spin down. Their rate of spin can get lower and lower over time if stuff is somehow able to extract its spin. Okay. Now, like I said, black hole mass, there's no limit to, right? You can have arbitrarily small and arbitrarily large black hole masses, but it's not quite true for spin. Theoretically, we think that there's a maximum limit on how fast you can spin a black hole. And if you were to spin the black hole faster than this limit, the event horizon would disappear. And what you'd have is what we call a naked singularity. And this is just one of those like problems in physics where Einstein's theory breaks down and physicists don't like singularities. So we you know, it's by no means decided, but generally the thought is that nature abhors singularities, and therefore singularities shouldn't happen in nature. Again, we don't know this for sure, but so we sort of think that black holes can only spin up to some maximum value, beyond which they become a naked singularity, and that's not good. Okay? And there are limits to spin of other things too. Like you could imagine spinning the Earth up so fast that it just flung itself apart, right? So generally objects in astronomy do have limits to their spin. And this is sort of analogous to that. If you spun it up too fast, its event horizon would just go away. Okay. All right, so now there are kind of two types of black holes that I alluded to earlier. There are these naked black holes and clothed black holes. Most black holes out there are naked. And what I mean by that is there's no gas near them. Okay? They're just on their own, and you would think completely undetectable. But if we happen to have two black holes orbiting each other in a binary system, as they the system is emitting more and more and more gravitational radiation, and that shrinks the orbit of the binary and causes the black holes to merge over some amount of time. And this is what we've observed recently with LIGO, is the gravitational wave signature of merging black holes. Okay? So again, most black holes are naked, and kind of by definition, a black hole is undetectable because not even light can escape. But if you get lucky and you can find them in binary systems like this, you can observe this gravitational wave radiation from them. So as these masses are being accelerated, right? Motion in a circle is acceleration. As when you accelerate a mass, you radiate gravitational waves, and I'm going to play this one more time. As you accelerate faster and faster and faster and faster, not only the amplitude of the gravitational waves gets stronger, but also the frequency gets higher, right? The wave crests and troughs are closer together. And it's this signature, this gravitational wave signature, that LIGO observed. Okay? What you see here is that gravitational wave ripple is passing through the Earth in two different locations, here in Oregon and here in Louisiana. And over the, from this whole, on the x-axis here, I'm showing time in seconds. So this whole thing is played in real time. It's about a half a second. And this is showing the frequency of those gravitational waves. So the frequency increases as the two black holes come together to merge and produces this chirp. So if we turn it to sound, uptick in frequency. And this exact, what we call waveform, so this is showing what that waveform looks like. This exact thing was observed simultaneously, or very nearly simultaneously, at two separate locations on Earth. And so you can confidently say that it's not just noise in the detector or some fluke, it's a real event that happened. And since then, we've observed several of these, many tens of them. And the thought is we're going to be observing something like one black hole merger every single week with LIGO. Periodically, LIGO goes down and comes back up, goes down, comes back up for maintenance and things like this. But they've already discovered something like 20 black hole mergers. And this is the signature of that merger. And embedded in that signal is information about the spin of the black hole that results. Okay? So imagine here we've got these two black holes that are going to merge together, and these yellow arrows are showing their spin vectors. Okay? So the thing's spinning sort of like this. These are both spinning like this. And this is showing the binary angular momentum, which just means how these two are orbiting each other. So they're orbiting like this, okay? And what LIGO can measure is if you add these two spin vectors together, like that, and then project them onto the binary angular momentum vector, like that, that's the spin that LIGO can measure. So it's kind of like it's sort of like indirect information. It's not complete information about the spins of these two individual things, and it's not complete information about the spin of the black hole that's left over, but it gives you something, okay? And so like if this, and I should say this can go between -1 and 1. So if this is 1, that means both the black holes are aligned and also aligned to the binary. If it's -1, that means both the black holes are anti-aligned to the binary. And then values in between, there are lots of combinations of these orientations to produce Here I'm plotting that is what's called an effective spin parameter, that kind of information about the spin of the black hole that results against the mass of the black hole that results when the two things merge together. And this is all the observations we have so far. There are a couple more not yet published results that find a few more at pretty high spin and one more at very low spin. And this is starting to build up some statistics of spins of black hole mergers, but we can't really say anything conclusively yet with these data about sort of the distribution of spins or even like typical masses or the distribution of masses of the leftover black hole. But we're getting there, and we should have many more sources as time goes on. So this will build up very fast. Okay, so still early days for spin measurements from gravitational waves, which again I said were these naked black holes. But in some cases, we have what are called clothed black holes, or what I'll call clothed black holes. And this happens when you have a black hole at the center of this thing here, okay? And it's in a very tight orbit with a companion star. And I mean very tight, like, some like 0.1 AU or something like this. This is interior to the orbit of Mercury. So imagine having a black hole that's 10 times as massive as the sun, orbiting our sun closer than Mercury is. Okay? Well, if you do something like that, the black hole can start ripping gas off of the companion star through tidal interactions. So it's the same idea like how the moon tugs on the Earth a little bit to cause tides on the Earth. If you imagine that either the Earth puffed up a lot, so now the stuff is less gravitationally bound to the Earth, the moon could just very easily rip it off of the Earth, or if alternatively you replace the moon with something much more massive, then you could rip, the Earth apart that way too. That's what's going on here. The black hole is just ripping gas straight off of this star, and because the whole thing's rotating, you form a disk around the black hole, okay? And the gas really close to the black hole is incredibly hot. We're talking like 10 million degrees. And when you're that hot, you emit X-ray light, okay? And that's how we observe these things. That's how we discover them. So usually, not much is going on in one of these systems. They're very faint. Often we don't even detect them. And then one day, boom, they go into outbursts. And we just see this huge flash of X-ray light. And it's often the brightest X-ray source in the entire sky. And so they're kind of easy to find that way. And that's how we discover these clothed black holes. And the term for these are black hole X-ray binaries. Black hole because black hole at the center here. X-ray because X-rays are being emitted from the disk. And binary because it's in a binary system. Black hole X-ray binaries. Okay. As a side note, I think this is incredibly cool. There's a guy, his name's Rod Stubbings. He's an amateur astronomer in Australia. He's got a backyard telescope that's pretty impressive. And in 1999, he witnessed a black hole. And again, when they get bright in X-ray, they often get bright in optical too. He witnessed a black hole go from 14th magnitude, okay, to 8.8 magnitude. All right. No one seems so impressed. But what that is, that's like if the very faintest star you could possibly observe with your naked eye, all of a sudden became as bright as the North Star. That's what we're talking about. And as far as I know, he's the only person to ever, like, with his eyeballs, looking through a telescope, witness a black hole going outburst. I just think that's really cool. All right, so we got into it a little bit, but let me dig a little deeper into the anatomy of one of these black hole X-ray binaries, or clothed black holes, as I'm calling them. We've got a black hole, of course, right? And there's this region called the rotate with the black hole. That twist of the space-time is very strong in this ergosphere region. Okay, but it's pretty close to the event horizon of the black hole. It's not so far away from it. All right, there's this really special location over here called the ISCO, which stands for the Innermost Stable Circular Orbit. And what that means is if I have gas orbiting a black hole, there comes a point, if I get too close, that a circular orbit is no longer stable. This is just a weird, quirky thing that comes out of general relativity. You cannot maintain a stable circular orbit if you get too close to the black hole. And what that means is all the gas in this disk that's beyond the ISCO can happily rotate, can happily orbit the black hole, but any gas interior to the ISCO, all of a sudden, is just forced to plunge right into the black hole. So once you cross the ISCO, you cannot orbit the black hole for very long. You are doomed, you're going to fall in, and then you're going to cross the event horizon, and then you're really stuffed. Right? Okay, now, why am I telling you about the ISCO? It turns out this location of the innermost stable circular orbit is entirely set by the spin of the black hole. So, the faster the black hole is spinning, the closer and closer this disk can creep in toward the black hole. The ISCO is smaller as if the black hole is spinning faster and faster and faster. If the black hole is not spinning at all, the inner edge of the disk gets this close to the black hole. And it turns out if the black hole is spinning in the opposite sense as the disk is rotating, the ISCO gets pushed even further out. Okay? So we say that the spin of the black hole can go from -1 all the way to 1 in these non-dimensionalized units that we use. So when the spin is 0, it's not spinning, this is where the ISCO is. If the spin is negative, that means the black hole is spinning in the opposite sense to what the disk is doing, rotating around it. Okay? And that's when the spin is negative. And the spin is positive if the black hole is spinning in the same sense as the disk is orbiting the black hole. Okay? So black hole spin can go from -1 to 1. And that's what I'm showing you on this axis here. This is the black hole spin parameter going from -1 to 1. Right? And when it's positive, we call it prograde. And when it's negative, we call it retrograde. And this is the location of the innermost stable circular orbit, ISCO, in some unimportant units. Okay? But what you see is that the ISCO can go from 1 for a maximally spinning prograde black hole, all the way up to 9 for a maximally spinning retrograde black hole. For a black hole that's not spinning at all, 0, the ISCO is at 6 here. Okay? So the important feature of this plot is that it's what we call a monotonic function. What that means is, if I choose any value for the ISCO, there is only one value of the spin that corresponds to. Okay? So like a parabola, for example, is not a monotonic function. If I had a parabola, some value of y here would correspond to 2 values of x if it was a parabola, right?
Yep.
But that's not what we have here. We've got a monotonic function. So that means if somehow we can measure the location of the ISCO, then we can just read off the plot what the black hole spin is.
Wow.
Does that make sense?
Yep.
So, if we measure the ISCO, that's equivalent to measuring the black hole spin. So the trick, or the name of the game, is to do our darndest to measure the inner edge of this disk. Okay? Because it tells us the spin. All right, and there are 2 techniques to do this. I'm going to take you through both of them. This is a very complicated diagram, but I'm going to explain it to you step by step here. Again, we've got our black hole, and we've got a disk around our black hole, okay? that disk emits light, X-ray light, because it's really hot. The disk is emitting light, but there's also this weird thing that we don't really know the geometry of, we don't know much about it. We call it the corona, okay, in analogy to the sun's corona. And the physical properties of the corona that we know that it's pretty compact in size, meaning like it's, in the near vicinity of the black hole. We don't think it spreads out really, really far. And we also know that it's even hotter than the disk. So we think the corona is, like 1 billion degrees or something ridiculous. And it's all just electrons flying around everywhere, okay? In the disk, it's hot, but it's not super insanely hot, okay? There are still atoms that can exist in the disk. For example, you can have iron with a couple of electrons left over. So you can have iron that's not fully ionized yet, okay? So you've got some iron in the disk, and you're emitting light from the disk, okay? That light interacts with these electrons in the corona, and what happens is the electrons in the corona give the light, the photons, some energy, okay? So these photons leave the disk, they interact with the corona, and they get way more energy than they had. The electrons lose some energy, give it to the photon, and also cause that photon to be scattered in some direction. Changes the direction of that photon. So it gives it some energy and sends it off in some direction. All right. So sometimes that direction is, just who knows where. And sometimes that light gets directed back down toward the disk. So what you've done, you've sent the photon here, boosted its energy, and sent it back down toward the disk. Okay? Now, that high energy photon can interact with the iron in the disk, and it can knock out an electron in the inner shell of iron, and iron doesn't like that. That's a very unstable configuration, and so another electron is going to want to come and fill that empty vacancy. And when that happens, when that electron fills that empty vacancy, it emits a photon at a very specific energy. Okay? And maybe we get lucky and it's emitted toward our eyeballs. All right. This is exactly the same physics as what happens in I think what's called X-ray fluoroscopy in the medical field. It's the exact same physical concept. Okay? You shine some high energy light onto the substance, you knock out these inner shell electrons, they get replaced and emit photons at a very specific energy. Okay. All right, and what we end up seeing is, like I said, it gets emitted at a very, very specific energy. So ignore this bump over here for now. Most of the photons come out at this very specific energy of 6.4 kilo electron volts. All right? Normally, if we have this kind of atomic process, we would just observe what we call an emission line. Okay? And we see lots and lots of light at 6.4 kilo electron volts. But we're very close to this black hole. And that does funny things to the shape of that emission line. The most important effect is something called gravitational redshift. Okay? So the closer and closer we get to the black hole, so here we're pretty far away from the black hole, and again, all the emission of this iron is coming from these inner regions of the disk here. So here we're not so close to the black hole. We get a little bit of distortion toward red. Red is that way, okay? Lower energy. A little bit of a gravitational redshift. If the edge of the disk creeps a little closer, we get a little more gravitational redshift. And if we get really close to the black hole, we get this really strong distortion. Okay? So what this technique relies upon, and it's called X-ray reflection spectroscopy. It relies on measuring just how distorted this red wing of the iron line is. And to show you what like real data of this look like, this is an example of like the very best data set we have. This is that red wing of the line I'm showing you here. And again, just compared to the prediction, looks something like, right? This is just a prediction, not real data. It looks pretty similar, right? So we think this is really what's going on. And we think this is actually a viable way to measure the spin of a black hole. Okay, and so the great thing about this technique is it can be applied to black holes of any mass. It turns out it's independent of the mass of the black hole. Here I'm showing you results from applying it to supermassive black holes. So the mass here goes from, this is black hole mass in units of 1 million times the mass of the sun. So 1 here means 1 million, and 1,000 here means 1,000 million, which is a billion. Okay? So these are black holes at 1 times the mass of the sun. This is a billion times the mass of the sun. And this is that spin parameter I was telling you about that can go from -1 to 1. We don't observe any that are below 0, which is a little curious. And most of them tend to be up at 1 for these supermassive black holes. And that's telling us something about how supermassive black holes form. The formation history of supermassive black holes, we think, is imprinted on their spin. And again, I can talk more about that later if people are interested. Okay, so we observe a lot of these to have a spin of around 1, which is the maximum. But there's a little caveat here, which, if you look at this picture, the closer and closer and closer you get to the black hole, the brighter and brighter and brighter you can be. Okay? So, in this example here, a non-spinning black hole, when you take a piece of gas and you bring it from far away to close to the black hole, you're converting its gravitational potential energy into light at an efficiency of about 6%, which is, I think, 50 times better than nuclear fusion. So this is the most efficient process known to man for converting gravitational energy to light. So this gives you about 6% efficiency. This gives you about a 30% efficiency. So there's a selection effect here. In other words, it's easier to see high spinning black holes because the disks around them are brighter, right? So that's what this line is trying to show. This dashed red line is showing, if you just assumed we had, if you say all the black holes we can observe just have a uniform distribution of spin from 0 to 1, they're equally likely to be spinning 0.1 as they are to be spinning 0.9, as they are to be 0.5. If you take into account this bias that you're more likely to see the high spinning ones because they're brighter and easier to see, you'd expect that the number of black holes that you find with a given spin, so right, spin of 0.4 is here, spin of 1 are these, easier to see high spin ones. The red line is sort of what you'd expect to see. And so this makes it look like all the black holes are spinning maximally, but it turns out it's actually consistent with a distribution that uniformly samples all spins. So always in astronomy you have to be thinking about selection effects and biases like this. Okay, great. So that's method 1. How about method 2? Am I good on time? I can't really see. Okay. I've got maybe 5 more minutes or so. Method 2 is what's called the discontinuum fitting technique. So you might be familiar with observing stars, and they're either kind of blue or red or yellow. They can have different colors. And the reason for that is when you have a body that's in thermodynamic equilibrium, like a star. It emits what's called black body radiation, and that kind of manifests as a certain color. Okay? So in this case, these curves are showing what the black body spectrum looks like, and it's entirely determined by the temperature of the star, or of the object. So a blue star might have a temperature of 12,000 degrees, okay? And its black body spectrum looks like this. A red star is cooler, has a temperature of 3,000 degrees, and its black body spectrum looks like this, okay? So we know what these black bodies look like, right? And we know that they only depend on the temperature of the object that's emitting the light, okay? All right. Now, we've got these disks of gas around the black holes, all right? With that in mind, let's think about this disk of gas around a black hole. It turns out that the temperature is not the same everywhere across the disk. On the edges of the disk here, it's much, much hotter, which is shown by red, and further away, it gets cooler. So there's a radial profile of temperature in the disk, all right? But if you take every single disk annulus and you say, what's its temperature, and what's the black body, the individual black body corresponding to that temperature, and you just add all of those up across the entire disk, then you get this green line, which is showing the spectrum, or the continuum, we call it, that's emitted by the disk. Okay? And a parameter in this spectrum, in this model for the continuum emission of the disk, that inner radius, that ISCO, is a parameter in that model, which is equivalent to saying that the black hole spin is a parameter in this model. There are several other parameters. You need to know the black hole mass, the distance to the black hole, the inclination of the disk. Is it edge on or is it face on? But there are ways to measure those things. And if you have independent, confident measurements of all those other parameters, then maybe you can fit your observed data with this model where the spin of the black hole is a parameter. And this is sort of what it looks like for real. All these kind of like points like this are showing the real data. All of these like crosses are the real data. And the solid lines are the models. And what you'll notice is we actually only have data. The data stops here. It's very hard to observe anything in this, what we call the soft X-ray or the UV. So you do your best to use these data and take your models, fit the data, and try to work out what the spin of the black hole is by fitting this discontinuum emission. Okay? Unfortunately, this technique only applies to those stellar mass black holes. It doesn't work for the supermassive black holes because it turns out this disk spectrum, this continuum for the supermassive black holes, peaks like over here. And like I said, it's really hard to get any observations in the UV or the soft X-ray. So we just can't see those disks, that disk emission around supermassive black holes. Okay, so we say, fine, let's take these two independent methods for measuring black hole spin and take all the black holes we possibly can and apply both techniques to those black holes. All right. It turns out there are 6 black holes where we've done this, used both techniques to measure their spin. On the x-axis here, I'm showing you the spin result. Again, 0 to 1. 1 is maximally spinning. This is the black hole spin measured with method 1, the X-ray reflection technique. This is the black hole spin measured with method 2, the discontinuum fitting technique. If you lie along this dashed line, that means the two techniques agree with each other. So these 3 sources up here, which are all maximally spinning, they have spin of, 1, 1. Both techniques agree that these are spinning fast. They're maximally spinning. But for these other 3, the techniques disagree with each other. Well, where does this leave us? Right? You can kind of have one of two attitudes toward this. You can be a pessimist and say, well, shoot, we don't know what we're doing, and it's hopeless, and we should give up. Or you can be the optimist and say that, okay, we're doing our best, and we're improving these spin measurements, and the data are getting better, and maybe, we can use these results going forward to help us improve upon the techniques and hopefully converge on an answer. And it's important to tackle this from two different approaches. Otherwise, how can you trust the results from one technique alone, right? So it's good that we're doing this. I'm an optimist about it. And really, this has only been going on for the last 20 years or so, attempts to measure black hole spin. And it's got us thinking as a community a lot more about the weird things that spinning black holes can do. So what I want to leave you with is a really big result that came out only about a month ago, having to do with black hole spin doing weird things in astronomy. And it's a little video, I think it's a minute long. I'll turn up the volume as loud as I can and play it for you. And that's what I'll leave you with.
The V404 Cygnus system, 7,800 light years from Earth, from the constellation of Cygnus. A black hole, 9 times the mass of our Sun, speeding on a nearby companion star. In 2015, the black hole started feeding very rapidly. The inner part of the accretion disk was puffed up with the intense radiation. We observed high-speed plasma clouds from the black hole's jets moving away into space. We saw only the brightest bursts of plasma. And usually, the jet direction is changing rapidly. The black hole's rotating about a different axis to the binary orbit. It then spins around like a top, redirecting jets. The intense gravity of black holes is enough to warp space-time. As the black hole spins, it literally drags the fabric of the universe around it. This is what leads the inner disk to precess. The black hole in V404 Cygnus provided new insights into accretion disks and jets, some of the most extreme phenomena in our universe.
Great. Well, thank you guys, and I'm happy to take any questions that you have. Wait on the lights. There we go. So the question was, for these stellar mass black holes zipping around our galaxy, how do we measure their mass? Okay, it's a really good question. The way we do it is we have to catch one of these black hole X-ray binaries when the X-ray emission is not very bright. So when these things are dim in the X-ray, we say that the system is in quiescence, and actually it spends most of its time doing that. And the reason we want to wait for it to go into quiescence is because what we're hoping to do is observe the optical light from the companion star, okay? And as the companion star will emit light, all right, and orbit around with the black hole, and we're observing the optical light from this companion, and every now and then, that disk is still there. The disk around the black hole is just not terribly bright. Every now and then, maybe it eclipses the optical light from the companion star. And we can see little dips and brightenings, of the companion star's light, and use that kind of information to dynamically work out parameters of the system, like the mass of the companion star, the mass of the black hole, the orbital period, the inclination of the orbit. So at the end of the day, we use the light from the companion star and information about eclipses to measure those sort of things, like the masses.
Follow up on that?
Yeah.
Does that mean then that all of these stellar mass black holes in the galaxy are clothed?
All of the ones we've discovered.
All of them
Yeah, but we think most of them are just zipping around by themselves. Virtually undetectable. There's a technique called microlensing that one might be able to use to find isolated black holes, but it hasn't been convincing. There's not a convincing case yet of discovering isolated naked black holes.
How do you measure gravity waves?
So that's a very good question. Okay, so there's this experiment called LIGO, and it's literally trying to measure, like if I have a ruler like this, okay, and a gravitational wave passes through the ruler, it will literally compress and expand the ruler, okay? It will distort the size, physically distort the size.
So it's not electromagnetic.
No, it's not electromagnetic. So we try to measure these teeny little compressions and rarefactions of space. And you have to do it to 1 part in 10 to the 21. It's incredible. It's insane. Yeah. But you're measuring distortions in the length of something, or in the size of something. And, yeah.
Are black holes, the black hole itself small enough that quantum dynamic effects are involved there?
So this is now outside of my expertise for sure. But yes, like what happens at the singularity of a black hole, or what happens inside of a black hole? That's a huge open question that we don't know the answer to.
Well, to follow up on that, wouldn't it have 2 spins then? So like an electron can have
Oh,
opposing spins.
so it's not really like it's not quite the same as like a quantum mechanical spin. It is. I guess it's not like electrons have one spin or the other. Black holes can have more of a continuum of spins.
On the second method, this method, the temperature profiles, those slices going out, is that modeled theoretical, or it's from physics, right? You can't actually measure that or see it.
It's modeled. It's theoretically modeled. So there's a prediction based on a theoretical model for how that temperature should change with radius, and there have been attempts to verify whether or not that's true, using really clever techniques called continuum reverberation mapping. So like if you have a disk and I have a flash of light, so if I'm the black hole and there's some like light bulb above my head and it flashes and shines down on the disk, that light will get to here faster than it will get to here in the disk. And so what I can observe, I can say, okay, the light gets to here and is reprocessed and reacts to that flash. And then sometime later, the disk over here receives that light, it gets reprocessed, reacts, and there's a time difference between when I see this response to that flash. And I can try to use that information to learn about the temperature profile of the disk. And it turns out, we might not know the temperature profile of the disk. So there are really interesting results using this technique. It's very tricky because you need to know things about like the atmosphere of the disk, but it seems like it's so hard to say. Like there's evidence that we don't know the temperature profile in the disk for disks around supermassive black holes, but the disks around the stellar mass black holes behave nicer. But yeah, it's theoretical model. We don't know for sure yet. Yes.
Recently, there was a picture of a black hole that was all on the media. Do you know anything about that black hole that the photograph was taken of?
Yep. So it's a black hole called in the galaxy M87. And you would think, so I mentioned it at the very beginning, it's a very massive black hole. It's 6.5 billion times the mass of the sun. And because it's so massive, its event horizon is pretty big. So remember I said the black hole at the center of our galaxy is only 4 million times the mass of the sun. Its event horizon is really small. It turns out, like, we're able, the size of that event horizon on the sky, right? The size of a black hole on the sky is going to depend on how big the black hole is and how far away it is from us. So it just happens to be that the black hole at the center of our galaxy, which is much closer to us, right? But it's small. It's like 4 million times the mass of the sun. It's small. It's like this big on the sky. This other black hole that's 1,000 times more massive, maybe its event horizon is like this if we put it at the same distance, but really it's much, much further away because it's in a different galaxy, and so it happens to be the same size. It's sort of coincidental, like how the size of the moon on the sky is the same as the size of the sun on the sky.
It's so much closer.
You have a picture of that black hole, don't you?
I do. Let's see if I can.
Yeah, let's see that. There it is.
There it is.
That's it, thanks.
I would like to know the effect of the black hole on the expansion, on the speed of expansion of the universe.
Oh. That's a good question. I'm not going to give you a satisfying answer, I'm afraid. I don't. I mean, yeah. So how do black holes work in the cosmologies? I suppose what you're asking. So people don't know what dark matter is, okay? And what sets the expansion of the universe is whatever is dominating what's called the energy density of the universe at that time.
Because it has like a ripple effect on the space-time, so it should compress the time.
Oh yeah, so if you're near a black hole, time does wonky things. But that's only in the very, very close vicinity of the black hole. If you're not close to the black hole, then there's no crazy effects on time or on expansion rates or anything like that.
Does the emission of Hawking radiation have anything to do with ability to determine spin?
No. So the only thing Hawking radiation is relevant for is like the ultimate fate of the universe. So in some ridiculous amount of time, like seriously ridiculous, like 10 to the 100 years or more, like nuts, 10 to the Google, you know? At some point around then, the only stellar-like objects remaining in the universe will be evaporating black holes. And they're evaporating through Hawking radiation, but it just takes forever. Yeah. So the timescale for that is just very, very, very long.
The Australian astronomer who saw the black hole,
Yeah.
know that's what it was, or did you think it was a supernova? Like I would have thought it was.
Yeah. So at the time, no one knew. It was that source is so incredible, and it's actually what I've been spending the last 6 months exclusively working on. Is that system? It went into outburst in 1999. Rod Stubbings caught it in the optical. Every single telescope in space and on the ground pointed at it. Very shortly after that optical flare, it got insanely bright in X-rays, and then decayed really, really, really fast. Following up that source later on, using these techniques I mentioned earlier, looking at the optical light from the companion star when it wasn't doing this crazy flaring stuff, that's when, so it does this crazy flare, and it's like, ooh, that's an interesting source. So then we followed up later, studied the optical light from the companion star, and we can work out the masses, and you say, wow, the mass of the companion is 6 times the mass of the sun, it has to be a black hole.
It seems to me that it would be very hard to get a black hole that doesn't spin.
Yeah,
Because the star is spinning when it collapses.
I agree with you.
So, do you think that all of the black holes that we'll see do spin, or are there some that don't?
You're asking I agree with you. I think it's very hard to get a non-spinning black hole.
Oh, we got one more question. Sure, sure. One more question. I'm sorry.
I'm happy to, if people want to come up and ask questions, I'm happy to answer.
Is there one more question?
I just wanted to know, is the event horizon for that black hole in M87, is it the edge of the event horizon, say, the orbit of Pluto? Or is it the orbit of Voyager 1?
So we don't know for sure. We think this is something called the photon orbit. And we think the event horizon might be slightly anterior to that, but we don't know for sure.
Thank you.
Yeah.
Good
Thanks so much,
question.
Greg.